which one is which? Mary, Maria, is it Mary or Mai? Mai, can you explain the yeah which you were saying and then Kasada? Kasada was saying no and Mai was saying yes. So, eh? Which one? Which one? Oh, she's back. You always have psychology and dynamical system. You do psychology. Which one? Psychology is wide. Environmental psychology, social psychology, education psychology. Special needs. So it's now that you are discussing that speech impairment is not the one who says, but in the ears of the world. Okay, now you trust what I was saying. Okay, so I didn't do anything concerning your work in the weekend. I made sure that I enjoy my weekend, nothing concerning material stuff. Eh? You too. You too, you have that liberty. Like you have liberty to say I'm not doing anything concerning my degree. Me, it is my career work. You, it is your degree. So you have to choose wisely. You have to choose your choices. You have to make your choices wisely. So last week we were able to confirm that if we have a coil and we make current flow in this coil, then some distance away from this coil, we can get some magnetic flux density. And we say this magnetic flux density will be the same as mu naught I over, if you remember, you can tell me about that, over 2 in S squared plus X squared 3 over 2. And this was the Z along the Z. This was X, and the radius of the coil was smaller. This was just to use what we did in electrical magnetism, but here is basically to show that we can have some effect from some point here, so that we are able to feel some magnetic flux density. Because at the end of the day, like I've already said, we are interested in how we can have these two babies here transported, and this one will be for the purposes of communication. With those two, once you cross them, we cross B, then we get the Poynting vector, which is the energy flux. So we can use this energy to transfer some. Just like we did for the electric field, where we tried to curl up the electric field lines and then tried to divert them. So are we going to do the same thing? If we try to divert magnetic fields, what happens? If we try to curl them up, what happens? The moment we get that, then we shall reach a point of curling them again, whereby we shall be looking at the curl of E, and the curl of H. Because once we reach a point, if we reach a point of, for example, the subwoofer, we may need to curl again. This, whatever was busy moving in this, we may need to curl it again and make sure fitting. And also when we are transporting out, we would want to curl it and make sure it goes through it. So to begin with, we first divide the magnetic fields, and then it creates a curl. So the divergence and curl of the magnetic flux density B. This shall be helped by the Ampere's second law. Ampere's second law. And this, if we consider a conductor like a wire, if this was a wire going through this cardboard, when Ørsted sprinkled a bunch of iron filings is not iron fillings, but iron filings. So for us who are friends of the garden, when you are going to the garden, you first sharpen the hole. You don't just go there. You have seen people with slashers and the guy is using energy as if he's going to kill somebody. If you sharpen that slasher to razor blade sharpness, you'll be just doing like this. And you'll finish a big part of your work. But you find a guy like he's sweating as if he thinks energy is what works. They say you take 3 hours sharpening the axe and take 5 minutes cutting the tree, or you do the reverse. You don't sharpen, you spend 5 minutes sharpening the axe and spend 3 hours cutting the tree. Which one is easier? So for us who are lovers of digging our own food, then you have to sharpen this part using a file, just like ladies file up their nails to make them look nice. So you have a steel, something which you sharpen. Those pieces which fall off are the ones which we call iron filings. The cleaner found them on my lodestone, my magnetic stone in the office, and she cleaned everything. That my stone was looking dirty, so she cleaned everything. Now the stone is naked, it has nothing on them. So when Ørsted put the iron filings and a little bit of shaking, then they align them into. The reason I came with this is because it has a semblance of the concentric circles. And using a compass, this compass was able to align consistently with the north pointing in one direction as they want. So this one would be if the current was upwards. But we can take a strand of this and take a distance from the center to the one of the concentric fields and take it to DR, and then find out what happens with the what we want in our case. So consider a straight wire. Consider a straight wire. In this case, like I was using my pen. Carrying I. Perpendicular to the page. Your page. Perpendicular in the blackboard. So since you are writing in your books, it's perpendicular in the page. So if we are perpendicular to the page or the blackboard, that means this would be concentric. So this would be our encircled X for the in. In is compared if you were having, for example, an arrow, and you are shooting at somebody. This is the arrow. Then if somebody was standing this side, they would be seeing an X. And if they were about to die, they would be seeing a dash. If you were in a radio and there are screws in the radio, and you are down there, I don't know what you'll be doing there, the screwer will be seeing an X. The one who is screwing, is he a screwer or what? And then the one who's being, one who is in the radio would be seeing the screw coming in a point away. So the same thing I have never seen a vacuum flask, you know. We don't have flasks for what? You just, if it is porridge, you just take life. And when it cools down, you let it ferment and take the good one. So a teacher is there saying a coke like that of a flask. I have never seen a flask. How do you tell me a coke of a flask? By the time I got my own flask is when I understood that this thing. But we had jerry cans. You get ideas, those of you are teaching. We had jerry cans. We could screw jerry, we could, you know, tighten the jerry can and unscrew, untighten the jerry can or uncover the jerry can. So you can use the jerry can instead of using a flask. Or for people who have never seen a flask. So if you are covering the jerry can, then you would be, as you cover, you will be going this way. As you uncover, you will be going this way. And when you are covering, the top of the jerry can will be going downwards to the jerry can. And when you uncover it, it will be coming up. So if it is coming up, you are recovering. So the fields will be like this. You are uncovering. You are covering the jerry can. It is going on the jerry can, the cover. So the field will be in this. But remember, I showed you the easiest way. Just draw the current. Draw the right hand side, it should be right. Put the arrow in the direction of what you have as the direction of current and complete your thing. If the current is downwards, draw the right hand side bit, put the arrow, complete your circle. So if we have these concentric circles for our current, due to the, our fields, due to the current that is in the page for you, and which is, so if it is going in, you are tightening the bolt, so it is going this way, so it will be like this. And then we complete. So then at a distance R, in a distance from this wire, we will say that, okay, not say that, but we got it as B is equal to mu naught I over 2 pi R. So from the integral, that the integral b dot dl over this any closed loop or circuit, if you took just one of these loops, then this would be the same as the integral over this closed loop. The b we have just got is mu naught I over 2 pi r, and then dot dl. Where C is a circular loop or circular path of radius R. So if we integrate, of course, this was bigger at the end. If we took a loop, this this B, I want you to be always careful. I don't want you to run anything, remember? This B is here. And the C is this NA of N loops we take of this for a distance R. And the DL is the path, is the length along the path. So we can take a tangent along this part, and this will constitute our DL. So our B, the DL, would be the same as our B, DL, and then what would be the angle between them? What would be the angle between the B, because the B is like this, and also the DL is a tangent. So at a given point here, this is our DL, this is our B. What is the distance? I mean, what is the angle between the B and DL? 0. So we got a pass, and this will be the same as B. That's why I don't have any dot here. It's not magic or preference. Where C is the path of radius, hence the B, the integral over the closed path C B dot VL would be the same as our B, which is mu naught I over 2 pi r times. So what would be the total length when you go around this closed path? The circumference of a circle of radius, so it will be 2 pi. So these ones would, and then we would say that so this implies that B dot dl integrated over the closed path C would be the same as the remaining part is the mu naught I. And this result holds for any closed path, holds for any closed path, C that is being threaded by this one, which would be threaded by current I. Threaded meaning the current is going through, so we have, if this was the current going through, this C here, any of this, that C would be, I mean this result here will be true for any closed path. Any of these, whether it is just here towards or here or there, as long as it is within the region that is threaded by the current I. In general, the integral of a closed path d dot dl would be the same as the mu naught, and the I would be the enclosed current we are talking about. Where I enclosed, this is equation 1 for this part, where the I enclosed Which one do you find comfortable? Ink or ink? Where I enclosed is equal to the, what is I enclosed of a curve C in terms of the current energy. So this, if this is a surface, if we take this as a surface that is housing this concentric, the field, the current through that surface would be the same as integrating over the closed surface J dot. Yes. And where S is being the open, this open surface here. Don't look at the white bit. These are the concentric field lines. But when we take the surface on which they are, the plane is this S, which we are talking about. If I have these, this is my demonstrating thing. This is, so we have these concentric circles. This plane here is the surface we are talking about. So, being the open surface, bounded by, so this, if this is our C, this is the surface that is bounded by the open surface, bounded by the C. Bounded by the curve equation 1 is equation 1, this one here is the notorious, okay, it's called, I don't want to have problems with the relatives of Ampere, it's called Ampere's second law. Ampere's second law. Once without being used. And which form is it? In integral form. In integral form. So this time I will get to both when I say state Ampere is a law in differential form, then you put an integral and underline. How does that work? So by Stokes theorem, and when we hear of Stokes theorem, we think of the line and the surface. Either from line to surface or surface to line. So by Stokes theorem, equation 1 becomes in equation 1 is B dot dl equaling to mu naught I would be the same as integrating over the surface S, and then mu naught, and I is sorry, before we do that, this would be, we take the curl of the vector that was being dotted with a line, and then we dot with the surface. So this would be the curl of the vector which was being dotted with a line, and then we dot it with the surface. this equation actually was equal to mu naught I. Thus, we can introduce back the I enclosed here, and this would be the same as integral over the surface S, curl of B, that ds would be the same as the mu naught I, which is mu naught I is the same as the integral over the surface S, J dot ds. So once you have this in integral form, you change it to a surface so that you can now bring in the curl. When you see the curl, okay, whenever you see a gradient operator, then there is curl by. So the differential peak starts showing up. So putting this together, since they are all loaded with the surface, we would have that integral over across the surface S, the curl of B, minus the other bit is mu naught J, and that with ds would be equal to, for any arbitrary surface of no dimensions we know, then we will find that for this integral to be equal to 0, the integral will be the one which is 0. Because that one is just an instruction. Therefore, this can only be the cause of the zeroness. And so that means the curl of B is equal to mu naught, and this is the differential form of, this is our second equation, and this equation 2, because of this maybe, something that got qualified, is the differential form of Ampere's circular law. Ampere has something like that. Ampere's circular law. So if I say state Ampere's, okay, the differential form of Ampere's circular law, and I see an integral, this time I'll call you for Keynes. Yes, because test 2, as we are covering things of test 2, we are done with the things of test 1. We got a note that it holds only for you can apply this for when? For steady currents. For steady current, if B equals to mu naught H. So the reason we say for only a steady current, if we don't have a steady current, then we will be having a change in current, if their time varies. So we will be having a differential this way, but we shall see better in a better way when we reach the next part. So if we have B equal to mu naught H, this would imply that the curl of H, the curl of mu naught H would be equal to mu naught J, so the mu naughts would cancel out. And this new baby we are seeing is what we call the magnetic field intensity. The magnetic try to curl the magnetic fields, when we curl the electric fields, they just disappear. Because officially, they should be able to be going out of a charge outward for charges. When we try to curl them, then you don't have a field around that charge. For the magnetic fields, when you diverge when you curl the magnetic field, you have two things to worry about. You need to know how much the current it was in that surface in which you are trying to curl them. You need to know how much of the current was threading that surface. And that field that was, current that was threading the field, the I per unit, the area in which it is threading, gives us the current. And then the other bit would be to know how much of the permeability that medium would be. For now, we are looking at a wire which was in space, free space, and then it had created the magnetic field lines. Comparatively, when we try to diverge, so we can only curl the magnetic fields, as we are going to see. When we diverge them, they disappear. We shall prove that. So comparatively, when we try to diverge the electric fields, we were worried about the charges, the charge density we have, and then the permittivity. How permittive would the medium be? So this ushers us to also first know what happens when we try to diverge these fields. You have the fields around the wire, depending on where it is pointing, and then you try to bend them off. Like you want to diverge them. What happens? They disappear. They're supposed to be going around, then you tell them go this way. They don't have much to go, because magnetic field lines should be complete from the north to the south.
A question.
Yes.
What is the difference between permeability and permittivity?
To permit, it has to go through. To permeate, it can. But that is English. You go to Google. I'm sorry. I'm just kidding. To permeate, if I put a magnet underneath this, I didn't come with it. I'll come with it for electromagnetic induction. When I put a magnet underneath here, and then I put this piece of when I put a magnet underneath and I put this piece of nail or pin here, then the magnetic fields permeate. I can feed it all over. Whereas when I have the electric fields, they should be permitted by this material first. This should be a material that can permit the electric field lines. Even if I put a plate here and a plate here, it's not any material that I put that would have these electric field lines going. It has to be either dielectric, first of all get induced, then permit the electric field lines to go through straight, be permitted. Whereas for the magnet, they can permeate. They can try to go around, even magnetize this fast and be felt some distance. If I put a magnet here and this is a sheet of metal, I can actually feel the magnetism here. They can permeate around. But I think the dictionary definition will make it more simpler for you. But I'm trying just to look at it in terms of the physics. So if we diverge them, these three lines, what happens? Any other question? When we diverge them, what happens? Yeah, we know they disappear, but why do they disappear?
Because they have to run from the north.
somewhere else. I mean, away south somewhere else, much as if I had a north somewhere, can I divert them to the other one? So, by the nature of how we got to feel something from the coil, we use bias valve. That the moment we are some distance away from the current, we can feel some magnetic field around there. We can expand this and see what happens. So the bias law for a general case of volume current distribution of density J can help us understand something. This was given as mu naught over 4 pi, and then we have the integral. We would have I dl, but now we would have the J cross R over R cubed, and then we shall, since we are talking of the volume, we have it as integral over the volume tau. The formula, this formula, I don't know which one they're comfortable with, the R then or NR then, gives the magnetic flux density, at a point P X Y Z in terms of the current density. J at some point, prime point P, X prime, Y prime, Z prime. To express it in terms of the diagram, so we have a volume. This have a lot of things here, but since I just need the volume, so I have a volume here, which is the one which is holding a current, and from this volume to some point P, at some point P, I'm having here, I'm feeling this magnetic field here due to a volume. So this volume here, whereby I need to, take an element of this volume, a simple cube, and then this cube, from this cube here is when I'm going to this point P. And so this is the volume tau. This is the elemental volume tau at point P, X, Y prime, Z prime. And then, of course, this is the position vector R. So we are saying that the formula gives the magnetic flux density at a point Pxy, Z, this one, unprimed. And then this one is due to the current density at primed coordinates. P prime, which is X prime, Y prime, Z prime. So we can explicitly state, that the magnetic flux density is a function here of the unprimed coordinates xy, and the current density is a function of the primed coordinates x prime, y prime, z prime. So the coordinates of the position vector would be x minus x prime, and that is along the I, plus y minus y prime along the j, plus z minus z prime along, and then the Benon volume, this is the volume, and since it is a volume, we are not, this is in the Cartesian coordinates x, y, z, so volume is length times width times. So this would be the volume here, because we don't expect any volume here. So this would be dx prime, dy prime, dz prime. So those are the properties of this analogy. That in order to know what happens when we diverge the magnetic fields, we first look at a volume current, or volume of current, which is considered, of course, when you carry charges inside that volume, and they are escaping, and they are hitting the surface of this volume, then you get the current density. And that current density, at some distance away from that volume, will be responsible for the field lines. And by Biot-Savart, we will be able to feel some magnetic flux density at a point, for example, R. So we have just explicitly confirmed that the magnetic flux density that we would feel here would be as a function of these unprimed coordinates. Whereas the current density, which is due to this volume current, would be a function of the primed ones. And then, of course, the R would be expressed in terms of unprimed and primed as the distance here minus that for I, y minus y prime for j, z minus z prime for k. And then the volume guitar would be dx prime, dy prime, z prime.
When you say magnetic flux density and then when you say H is magnetic field intensity, what's the difference between the two?
The difference is that the magnetic flux density is the same as, anyone remembering the simple formula? No, before you go to numeric, what is magnetic flux density? If you looked at a conductor placed in the magnetic field of length, a unit length conductor placed in the magnetic field at 90 degrees, then you will get the magnetic flux density as the force on this unit length carrying a current of 1 ampere placed perpendicular to, that's by formula. So this is magnetic flux density. Then it is related to the magnetic field intensity as this. So I don't know how, comparatively, we have what we call the electric displacement vector B, and then we have the electric field intensity E. So H is like a step sister to E. As the, would you say stepdad or what, or cousin? As the B would be the cousin of D. But there is a better definition for that than just saying that the difference is that. But they are related, the two of them are related in this form. For the actual definition, I think you exercise, get the definition of magnetic field intensity. Electric field intensity is the force per unit charge. For if you have a charge producing an electric field intensity, so electric field intensity would be the force that is experienced in this electric field per unit, the charge that is producing the electric field. So I don't have the actual definition off my head. But some people call it magnetic field strength. That's the other name of it. The magnetic field intensity, some people would want to call it magnetic field strength. Which one? H. H. Can I go on, Madam President? So this, the integration, now that we got all these things clear, and we have, of course, when we see J, we remember that for current to be related to J, I would be equal to integral J dot S. Then when we look at the B equal to mu naught integral J dot J cross R over the R cubed the tau, then we have an integral. So we need to know we are integrating with respect to who. So here when we are integrating with respect to who? Of these two animals here. Our integral is with respect to which ones? Primed or unprimed? We are looking for B here, so we shall be here. That's where we shall be collecting all the pieces from the volume that is going to give us the magnetic flux. We can't be concerned about the prime values. So thus, integration is over. Integration is over. Wait a moment. Before I mess you up. When we are looking for this thing here, is it here or here?
It is here.
Where?
When
we are here, we are getting everything within the effect of this. So is the integration when around here or in here? I want us to get it properly before we put it down properly. These are the small currents due to the charge that is flowing out of this volume that are eventually causing the magnetic flux density here. So when we are integrating, do we put these pieces together, or do we have to be concerned about the currents here or here? So the integration is over the primed, coordinates. And this is the P prime, X prime, Y prime. The divergence unprimed current. So the area will be around there. The divergence, we are already away from the volume. So we will be now talking of the divergence. But don't worry, the issue now is to do the algebraic gymnastics. So that's taking the divergence, of the equation of B yields B was equal to mu naught over 4 pi integral J cross R over R cubed in R. So we are now taking its divergence, which will be equal to the mu naught over 4 pi integral. Then we take the divergence of this whole bit, which is the J cross R over R cubed, and then beta. From the identities, so some time ago, I went to look for something. The lady serving me disturbed me, and I was very rough at her. And she exercised her rights and made me walk back to this place to pick a bank statement, which was not needed, but I picked it anyway. So when I was coming back on foot, I realized that I'm having a problem slowly by slowly, probably maybe because I sleep late, wake up early, and I think I was starting being irritated easily because of stress. That's why these days now I'm no longer concerned about these negative charges. Which just decided to say, we are going to screw you up in class so that every time you come, you always complain. So I made a decision that I will not complain anymore. So when something happens these days, I just take it easy. I play dumb. For Grace, from the time I attended your Connect, I gave up. I said I will not bother anymore. For her, she has a ticket to do whatever she wants. I just stamped, I said, this one can do whatever she wants, so I will not complain. So you can always sit there with the parasita, you the child, the fundamental. So using the vector identity, of, I don't know whether I got the vector identities here. So, but I think I got it. These days I've learned how to come with my drift. Drift has a black cover. So we're going to use an identity of the, using the vector identity. Is it 1 hour already? Just 1 hour. Yeah. When I start now talking, because I came, was it like 4 or 5 minutes past? It's now 5 past. So when an hour elapses, I'm supposed to be making some bread. Automatically, it's just in my head. So using the vector identity, that the divergence of the cross product of two vectors f and g. I want to first of all look for this. The divergence of B cross C, the triple products on the vector identities, the A dot B cross C. So which one should I put? Should I put the one in the book or the one in the note? Notes. You don't want to be confused. So when you cross, when you take the divergence, when you take the divergence of the cross product, then you get this one as being the same as D, then dot the curl of the vector F, then minus the F dot the curl of B. So we are going to let the F equal to J and D equal to, according to the notes, I think I made a correction. We let G, should I say start with G or F? Let F equal to J and G equal to R over R cubed, where this one here. So this is going to be our F, and this one here is going to be our G. So there is if it is not corrected in the notes, that's the correction I would want you to take note of. And so if that is the case, I can do it with you. So that means that we have the divergence of this here, which would be the same as, so the divergence of B is equal to the mu naught over 4 pi. Then we integrate over the volume tau, and then we now have the whole thing. And the whole thing is that we have G, which is R over R cubed. I don't have time to rest when you do your mathematics. Dot the curl of the J, then we subtract off the F, which is J, dot the curl of the R over R cubed. And then that one we say in, I want to run so fast towards the, but here I am putting in myself into this mess. So let me first do the identity and then make some conclusions from that. So the divergence of that is equal to that, which is equal to divergence of B is equal to let me try to write this equal to this after that. So that is divergence of J cross R over R cubed equals that. And this would equal to, do we have any variation of what is the gradient operator in this case? Is it for prime or unprime? We are current when we are diverging Benon, which has ended up in this. Here we have the gradient operator. This gradient operator, this differentiation is over where? The term was over, and J is a function of. So this would be the same as minus J dot the curl of R over R cubed, since the curl of J equals to 0, because J does not depend. Because J does not depend on unprimed kernels. Of EXY. So differentiating anything with unprimed in terms of, we are differentiating J with respect to the unprimed kernels would be an automatic 0. So that first part will also remain with minus J that the cross product, okay, the curl of R over R cubed. Furthermore, from your mathematics or mathematical methods in physics, minus R over R cubed is the same as grad 1 over R. Hence, the divergence of J cross R over R cubed is the same as minus J in the curl of grad 1 over R, and this is believed to be equal to, so since grad 1 over R equals to 0, see mathematical methods in physics. If you can't remember the notes, you go to Mary J. Boaz under the references. Thus, all this says that divergence of magnetic fields will be equal to. This is by calculus, but physically, if you try to diverge fields which were just going around the wire, you diverge them, you have destroyed them. That's why some of you, when you come here and your parents sent you to work hard, and then you get diverged to the clubs and to Acacia Mall and to go for concerts, you get spoiled In integral form, you denying the Pharisee. In integral form, is the chairman. So the integral b dot dl is equal to what am I writing in this? Where am I writing this? This is not part of the notes. This was there is nothing. The integral form. This was for the Ampere's circular law. I don't know why it appears here. Okay, so we now have understood how the not supposed to be here. So we now know the behavior of electric fields and magnetic fields in terms of if we want to divert them or concentrate them. Concentrate meaning curl. You want to curl them to get them concentrated to a given point for any purpose you want to move for, then we know what to do. If you want to push them far away, we now also know what to do. So, knowing all that, we can visit something that we use when we are doing the communication, which you study about in the microwaves and microwave optics. And by that time you'll be able to look at the waveguides. I should have done that in one of the, I think the last part of the course outline. If you are so interested, you can look at the transmission line. You are not studying just for passing the semester exams. If you want to be something, the time people put in, for example, when they are on TikTok or on Twitter, the time they put in to rehearse their videos, the time they take to make sure these videos are edited. But when it comes to a test, they can't sit down and read. And anyone who is a content creator here? Content creator. She's a content creator. You don't deny being content creator because everyone will be able to find out. If I go TikTok and put everything there until when I get to see the thing I don't like is TikTok. Is a messed up place. I normally go there and scroll through and just confirm that it's a messed place. And then if I take 30 minutes just trying to see what there is a medical doctor explains about medicine. There is a traditional doctor explaining about love. There is someone explaining about dreams. There is someone who just does stupid things. And there are these ones who are saying you have to be above 18. This is only for above 18. I don't know what that means. So then I just go out. I used to be, when I was on Facebook before it closed, it used to be, you know, you were able to meet your OBs, your OGs, and then me, I was using it for airing out my views, writing my, have you read that?
Yes, been busy.
Good. So you'll find when it is already removed because it was automatic. I had put it visible for a couple of days. This is where I get a problem with students. If I say there is a story, a man, a bishop or pastor, I think pastor, he visited their home. They had a check they were going to donate to that church. So when he came home, I think they kind of misplaced it. And then after he went, it was of either $10K or something. I don't know, it was good money. So when he went, they looked for the check they couldn't see. So they were like, so even pastors can steal. So they kept quiet. They kept quiet, they got frustrated, they refused to go back to church because this thief, how can you just visit their home and then the check disappeared? So as the man was moving at one point, he bumped into the pastor. And then the pastor was like, oh, how do you call the brethren? How do you call his brother in Christ? Something like that. He said, you are lost, I don't see you anymore. The man said, well, we have been busy, but well, there is something that disturbed us, you know, as a person who is disappointed and whatever, and who is a son of God. He said, oh yeah, my son, what happened? He said, the day you visited us, we had a check of this amount, and we were about to bring it to your church and disappeared. And we were a little bit disappointed. And this was after like 3 months. So the pastor laughed. He said, oh, my son. Well, I saw it when we were having a meal, and I felt it was in a misplaced place, so I got it and put it in the Bible. So that means you don't read your Bible. You can imagine for 3 months they had never opened the Bible to locate it, at least to land on the check.
Maybe they were still yes.
So this is the man who said, I want to read it. So I go home, I go to Mwere, I copy it from my hard drive, I paste it on Mwere, make it an article, and even write to him. Say, I'll put it there, the link is here. And after 2 weeks, he's telling me, I've been kind of busy. So we need to know what we call the magnetic potential. Magnetic potential, just like even we were led to look at the Laplacian's equation because we needed to see how so this is the electric potential. And so we need to know about the magnetic potential. So the magnetic vector potential, so there is a vector here. Yes?
I missed you were saying about something on that expression of the father. Where it comes from. Father, negative, with
So the but you saw me write this.
I thought that one was to give me why is blood one of the eyes.
If you don't get this as well, you come back. I'm not going to do mathematics. So but you want us to do that?
No, I was meaning that why are we equating it to? Why are we getting the R, negative R vector of R3, then R should be equal to that.
Okay, what is grad 1 over R before we go what is grad 1 over R?
Say that according to mathematical method is 0, grad 1 over R.
Before we go to since it is equal to 0, what is, if you were to differentiate it, what do you get? Just take one along, okay, take this grad to be carried by clear or DDR.
1 over R squared. Negative 1 over R squared.
So if we were to have this position vector to be, if we are to deal with magnitudes, what will be R over R2? Hey, that That's how life is. You have to invest time in these things. Otherwise, they would look abstract on a mere twist of stuff. Okay, so the magnetic vector potential, we know so far that the divergence of B equals to, no doubt, beyond the physical nature of this, the vector identity that the divergence of some curl of vector A equals to 0, then we say where this A here is the magnetic vector potential. So if this thing is equal to 0, and there is something whose this whole bracket also, when you take its divergence being 0, so we can say that this is equal to the B, but before we do that, we can reduce. Anyone who still has questions about why this equal this? This is R over R cubed, which is 1 over R squared minus. And when you differentiate this, you get the same. And when you now take the grad of 1 over R, you can choose to differentiate the numerator, which is differentiation of the constant. We divide by whatever we get, we divide by the denominator, and then we get 0. It's how people choose to get what they want, in any way they want. So according to Bayes' law, then we have a simple, we had a simple strand of the wire, and an element of this wire is causing a magnetic field at this point, P, X, Y, Z, and this was the element. The other time we had a volume, so if we now have a line with the prime here, this is the current I, this is negative, positive. Is the current going this way or that way? This would be moving this way. So the magnetic flux density that would be felt at a distance r from the element B at P would be the same as mu naught I. Sorry, mu naught over 4 pi, and then we have the integral J cross R over R cubed d tau. But we've just said the grad 1 over R is equal to minus R over R cubed, which is equal to, if we divide these two, R vector over R magnitude, you will get R roof, and this would be over R squared. You still have a minus there. So we can rewrite our magnetic flux density and then say that this implies that B is equal to mu naught over 4 pi integral grad 1 over R cross J d tau over the volume tau. You can call this one equation 1. If we use the vector identity, using the vector identity, we've had using another vector identity, then we have that the curl of FA is equal to grad F, which is now a vector, then crossed with the A, then plus F, the curl of A. And this is equation 2. I'm always mesmerized by how birds keep time. If Africans had sense, those who do biology may do physics, they would now be testing exactly what is that biological property that makes a chicken, no, a cock. The chicken are always not balanced. Makes a cock. Do you know of a chicken which tells time? It is only cocks which suffer to tell time. They are there announcing it is now this time. What time is it? Is it accurate or is it just clocking towards 1/2 This one is lost. This one is lost. We didn't do it at the top of the hour. Exactly. But he didn't do anything when the other hour had reached. Out of nowhere, just remembers. But I think it is a good research. It can come up with because exotic chicken are always confused. They are like every time, they don't even know what time it is. But ours, because of struggle, I don't think there is anyone. Do chicken in those housings where you rear them, do they make this noise?
No.
They are confused. They eat any time. They don't care. This one has to. I don't know. This one has to make sure that things are okay. It is overdoing it. Where F.
That's what is the kiss.
Where F is a skull. So this is just an identity which we can get from the book. And from the book, this identity is on product rules. The grad FG. No, not this one. It is, yes, under product rules, but number 5, which is the divergence of curl. So this is number 7. The curl of FA. So this is number 7. I don't know whether the one I gave you, number 7, under product rules. So I put the comparatively, this is our vector, and then we are having, so this one is grad, the curl of J, then we have 1/r, so F will be equal to, then we would have that the grad 1/r, this other part, cross J would be the same as the curl of J/r, then minus 1/r, the curl of J. So we make we substitute for that in our expression. But J, this is equation 3. But J is a function of, because it is where the current is on this circuit here. So it's a function of the prime coordinates. And the Brownian operator is a function of, remember we said divergence is a function of the unprimed. And the divergence is the one which is involving the Brownian operator. Operates on the unprimed. And this would imply that 1 over R into the curl of J would equal to we see the curl, if you this one is on unprimed and J is a function of prime, so you can't differentiate. It's a constant in a sense. So equation 3 becomes this one here. Equation 3 becomes this one disappears. So we get B in the notes it says reads. So I don't want you to crucify me. Is equal to mu naught over 4 pi integral over the volume tau, the curl of J over R tau. Then or we can write B equal to mu naught over 4 pi, then integral over the volume tau, then we have J over R tau. Then we take this one to be equation, what is equation 4? Equation 3 becomes, wait, equation, from equation 3 then we have that, equation 3 becomes, I think I skipped, who is on Moede so that, I do what? What is the rest? I think I'm tired. Let me first check how much I'm left with to finish what I want to finish. Huh? I can rest. You also want to rest? Yes.
How come that in the previous expression for when you were finding the curl of the divergence of B, you said that the divergence of 1 over R is 0. But then in this case we are ignoring that part of it being equal to 0. Does it only, is there a condition where it applies in that sense?
And when we are, you know, I think the template has given us some value.
Yes.
Where are you?
I'm saying here in the, okay, in the expression for B. Here, okay.
This one?
Yes, equation 1. We left it there, we found it, okay, we found this whole statement of equation 3. So I'm asking that in the other divergence of B, when we're getting the divergence of B,
So like you wanted us to immediately...
I'm asking because the other time we considered that, so is there a condition where it applies and here it doesn't apply? It being equal to 0.
What I can say is, I'm just going to look for a nice explanation. We choose things because of what we want to achieve sometimes. And why we are not making it 0 immediately. Fame, can you help me? Can you use your math and tell us why we are not immediately saying that since we got the grad of 1 over r equal to 0, can you allow me to look for a good reason next time? Not you. You are supposed to explain since you are the math. You remember I told you of a story where I used to want to explain everything. If I can't, then I scare students. Until when I was told by people who are humble enough to say, can I explain this next time we meet, if possible? So I'm also now humbled that I can ask for me to explain the reason why it behaves like that at this point. Kivayo. When we are here, I don't say the other thing. I say it when I meet you, when we are two. But famous thing, do you have any? But is it true that grad 1 over r is equal to 0?
Yes.
But also grad 1 over r is equal to minus 1 over r squared?
Yes.
How? And when? When we choose to say is equal to 0, when we choose to say is equal to 1 over r squared?
For grad 1 over r, when we are differentiating without any condition applied, automatically we take it normally.
Normally, so that is minus 1 over r squared.
Yes. But if there is a condition for, then it equates to 0.
Like which condition?
When R is a very big value.
Yes.
When r is a very big value.
It can go with the conditions.
Distance.
If the distance is very large, then you can take that to
Approximating.
approximate to 0.
So when the distance is very big, it just becomes 0 because it is one of a big thing.
Yes. One of the very, very big thing approximates 0.
Mathematicians. Kauma, what do you think? Am I being told the truth or convincing me to just...
Next time, later.
Kasada, what do you think? It's telling me that if R is not so definitive in terms of being large and there is nothing that is, we are taking it as normal, then we get the minus 1 over R squared. But if it is in ranges of being, remember when we had to say that at distances far away from the coil it behaves like a coil check, so like that, then she's saying that there it can really go down to 0. So what do you think? Any math major here?
Some sense.
Huh?
Some sense.
In some sense. I'm not asking you to comment what she said, but for you to give us where this comes in about.
Okay, mathematically what you say is correct, because if we are going to a very further point, that is, okay, now if we are considering physics, we are looking at that if we are diverging the magnetic flux density, so we are trying to move very far away from the radius, I think, of
The volume or the element, whatever element.
yes. So if we are moving far away, that is we are diverging far away. Is that what it is, that we are going to distances tending to infinity? So then that makes it be 0.
Which section of math is that?
small numbers and bring them like
Okay. Where, when you are on canonical ensemble?
No, in the introduction.
Eh,
Also in the mathematical, I tell you in the introduction to this thing.
okay.
Actually,
Edward, where are we now?
But mathematically,
Now I'm like the other old man who was in the...
correct that.
Wait, I first did I give a story to this class or another class? Another class. So this old man was in a Costa. Then the girl was answering the call. The Costa was going to Ginger. No, it wasn't going to Ginger. It was going to... They were going to Masaka. So one girl receives the call. Hello, we are in Namawajoro, but we are coming. I will be there soon. So a young man also was called, and the young man said, we are here at and I will be with you soon. So the old man said, excuse me, driver. Tuliwa. Where are we exactly? Because this one is saying this one is saying this. So I want to be sure. According to whom had I asked, where are we, Edward?
so I think what she's saying, I think it's okay, but still we need more explanation or more conditions must be stated.
Okay, fine. So tomorrow, by tomorrow, if not tomorrow, by next week, then I would have had enough time to go through. So now that I have a little bit rested, can I move on? Yes, someone said I should rest, so I've rested now. Can I now move on? So I had issues after saying equation 3 becomes, so it becomes grad 1 over R cross J being the same as the curl of J over R. So you take the curl, you take the R under here. And this one becomes equation 4. Then equation 1 for B, equation 1 becomes, or now reads, if you are in the notes, B equals to where we had this, we now have the curl, so mu naught over 4 pi integral over the volume tau, the curl of J over R, and we are integrating over the volume tau, or with respect. I think, is the integration with respect or differentiation? We integrate over or with respect? Both. Please get the language together. It can't be both. Or we get the, we can write B being the same as something that is missing in this expression, which I was wondering. So this B can be, we can have the whole thing. We can take the curl outside, and then we integrate the rest. So it will be mu naught over 4 pi integral over the volume tau, and then what will be left inside there? When we are taking the curl here, J over R, the tau. That's for purposes of value. And this one can be equation 5. B Equation 5 is in the form B equals to the curl of something which we call A. And this A here in equation 6, that is comparing equations 5 and 6. Then we have the A is equal to mu naught over 4 pi integral over the volume tau J over R d tau. And this is equation. This equation here is for what we call the magnetic vector potential, where A is the magnetic vector potential. The E is equal to 1 over 4 pi epsilon naught Q over R squared is what we call the electric field density. But V equal to 1 over 4 pi epsilon naught Q over R is what we call the scalar electric, the electric potential, which is a scalar. And this one is a vector. So now we see this electric potential. We now have a vector, a magnetic vector potential. And then we can say that if we take a line, then we can say that the J, since just want to be sure. Since J dot tau is equal to when you have J, I don't think it's J d tau. Since J d tau, what would be J d tau equal to in terms of the line? This is J, which is I over N. So this would be the same as I dl. True or false? True. This is I over N. This is A times D. Yeah, so the S will go. And then you have the idea. For line currents, so we can have this being changed into a line. So this would be, the vector potential would be the same as mu naught I over 4 pi. Then we would integrate over the length L dl over R. This is for when we have line currents, like if we just have current going in a line. But if we have surface currents, then we talk of the current density. And for surface currents and for surface currents, then A would equal to mu naught or mu naught over 4 pi. Then we have integral over the surface S, J dot ds over R. This is equation 8, equation where Js, here, this is Js, where Js is the surface current density. Okay, we don't need to bother this. The surface current density. If the current itself extends, the current itself extends to infinity, the current itself extends to infinity, equations 7, 8, and 9 what happens to them if R is so much big going to infinity? No longer hold. Special case, there are special situations. There are special situations where the magnetic vector potential may be maintained, may be sort of obtained from integral A dot dl being the same as integral A, curl of A dot ds, since the curl of B, curl of A equal to B. So we get the integral A dot dl being the same as changing to a surface B dot ds. What is B dot ds? The magnetic flux field lines in with surface area goes to the magnetic flux threading the surface. Magnetic flux threading the surface. This gives us a fertile ground or background for doing an example tomorrow, and then we conclude this part and look at magnetic susceptibility. Then if God allows, we do a magnetic induction, Newman formula, and then we shall now be ready to do Maxwell's equations. So I see you tomorrow.